Yeah, so basically, you can call me Roy. I work as a data scientist in Calgary. I finished my master's at UFC. Um, I've been a GDG developer lead for about 6 months now. If anyone has attended the Calgary Dev Fest, they would have seen me speak there. My research was about integrating VR and ML. And so I have done a lot of gaming workshops for GDG before, and this is the first time I'm doing an AI related series. But considering that's what I do in my profession, I like to share my experiences and get people to solve problems because, both in terms of job market and predictions for Alberta, it's very much on the horizon that AI is going to take off, and a lot of these big industries are going to start using AI for optimizing problems, in cost reductions being, starting of it. So I really believe that understanding AI and learning how to model problems and use it on data, and a lot of these organizations have a lot of data already, that will really help, not just in terms of jobs and in general, just to move the field forward, in terms of industrial applications. So that's why I'm doing this. Hopefully, everyone can learn something from this. So we kind of talked about before supervised and unsupervised problems. Supervised is something when you have a data set and there is a predictable or a quantity that you want to predict. It can be either like a class or a decision, true or false, or a continuous value, or multiple continuous values, which is like a distribution of proportions kind of a thing. um, so when you have this target variable that you would like to predict, then you can use the supervised machine learning context. Deep learning or neural networks is just one technique. There are many supervised machine learning approaches. We are currently focusing on the neural network aspects. Um, in unsupervised machine learning, you have things that do not come with labels, where you're generally trying to group things and extract patterns in your data to then, either manually label those patterns to do some decision work, or you may be just interested in terms of research or understanding the basic dynamics of things. You may want to just like analyze the patterns themselves and how they change across data sets or different conditions or over time, things like that. So one of the major areas of applications is in computer vision. Identifying faces, classifying different objects, are the basic applications, and a lot of work has been done in this area. And you wouldn't probably use any other approach to do this kind of problem in the state of the art, right? Like these problems have found so much success in this area that neural networks is pretty much the way to go. There are other experimental areas where classification and regression, where you're trying to kind of find values or predict things. Sometimes some other techniques, like logistic regressions and random forests, they give better results than neural networks. And then it's a decision process using different metrics, different you know thresholds of your expected behavior of a system, what your design constraints are, what your computation constraints are. So depending on many things, in practice you can try out different options. Um, so there are three basic deep learning frameworks: PyTorch, Keras, and TensorFlow. Now Keras has become a part of TensorFlow, and most of the um, recipes that exist in TensorFlow can be accessed in Keras or through Keras. So going forward, we mostly be focusing on PyTorch and Keras, but I'll talk about TensorFlow and what it is a bit more today. In general, these slides deck would kind of give you all the basic concepts needed to design neural networks. And if someone's attending this meetup for the first time, you might have a bit of a difficulty catching up. So I would really suggest looking at the first two recordings where I talked about how you design a neural network, what these each of these are neurons in a layer. Information is inputted, or your data, where your data is like this is an entire. Okay, and also that first link that I've shared, you can open the slides on your local system, so that, because once I start working on the notebooks, then you might not see my slide deck at all. So something like this is like your age, income, employment. This together is your one input X. And each of these are your X1, X2, X3, where these are all individual features. Now, they can be continuous values or they can be zeros and ones, depending on the kind of problem that you want to solve. You might have to convert these um, input features into one or the other. You might have an input feature like country, which is a categorical variable, uh, which is USA, India, Canada, all like in a list. You cannot really process that kind of an information directly. You need to then convert that kind of a feature into a categorical one, where one feature itself is just, is this Canada or is this USA or something like that. And so you can also, if there are like a finite number of um, like inputs in your continuous space. So if like age or number of website visits, it's something like 1 or 5 or 10 or 20, you have a finite number of these values, then you can also convert that kind of an input into, is it less than 5, is it less than 10, is it less than 20, that kind of categorical bracket. And depending on actually you might want to test using continuous values with against categorical values and see which model does better. We'll look into kind of these setups today. We did not do much of that in the last two sessions. So basically you have this neural network where each of these circles is a neuron. It has an activation on it, where an activation is basically a function. You have the data, which is your independent variable x, coming to this function, and then this function does an activation operation on it. And this operation is governed by the weights that's on these connections and the biases that is there as a design of this function. And this function outputs a value which is called the activation, and this then again has a weight which propagates to the next layer, and so on. There are many different architectures of neural networks. There are uh, the two main ones look at convolutions, or basically here you have these image representations, where whether you go from right to left or up to down, there are these features inside this picture, be it an edge or a shape or a kind of a gradient of change. That is what you're interested in. So that information within that image is relative with respect to each other or with respect to the pixels. So that is the kind of data that you get when you have an image processing application, and then you do a convolution filtering operation on it. So if you have an image that is 28 by 28 or 1000 by 24,000 by 24, and in a conventional network like this, you could then unfold that data into a 124 cross 124 long list, and that's a huge number of features. And if you did that, you would train that using something like a multi-layer perceptron, where each neuron was one pixel. So we can do better than that. We've seen experimentally that using something like a convolution operation on an image reduces the number of pixels that we can process or need to process. And that is the state of the art in this kind of an area. So here we have an image, and you can look at the previous session recordings and these links. So you have an image, and when you do this convolution operation, you're basically reducing a set of adjacent pixels into an interesting feature that is there in that box or in that region, and therefore you can reduce this several times into several different representations of these filters. And then one type of filtering, so if one filter was looking at edges, and one filter was looking at gradients, and one filter was looking at a shape, and those filters then themselves could have interrelations. Like when you have an edge starting and another edge ending, there is probably a gradient difference between those two edges. So those kinds of relationships, a secondary convolution operation on the filter outputs can generate. And then finally, once you're done with all these convolution relation extractions, you will unfold this into one list and feed that into this linear network, and then you will add dense layers and finally get a prediction if this image uh, is of a cat or a dog or something like that. So that is the kind of problems that we solved before. In this process, you kind of use these different activation functions, ReLU being the most popular one. And backpropagation is how you actually learn. So if you make a prediction of a cat and a dog, and if the true label was not a cat and a dog and was different, then you actually compute what was my prediction of this being a cat. Maybe it was zero point 0.6, but the true value is a dog. So what is this difference? And the other one was zero point 0.4, so what is that difference? And then you back propagate that. So the sum of these differences is your total loss, which is a scalar unit. And then with respect to the scalar unit, you back propagate what could have done differently in getting this result, to update the weights. So the result comes from these function nonlinear operations, and these functions are dependent on weights, and all you can control is your input, and your output is known. These weights self-learn, and you can design what kind of functions you input in each of these points. You can do other kind of design considerations, but you cannot control them in the learning process. So what you can do is, when you know that this is my absolute true label, and this is what I predicted, and there is an error there in my prediction. I can, based on this error, modify these weights so that the next time it does better. And this modification of weights is done by a backpropagation process. And different problems have different loss metrics, different activation functions. That is a convention that people use, and a lot of research has been done. There are many different articles and blog posts that talk about what problems are solved by what kind of formulation. And it is kind of depending on, once you have a kind of a problem that you want to solve, it's about looking through all of these resources that's available out there, and coming up and testing and trying different solutions. It's something like what developers do with Stack Overflow or with other blogs. It's kind of similar. This wasn't like this even a couple of years ago, but now the field of AI is becoming more standardized, and when you have more developer resources. So these kinds of articles and blog posts are really helpful in that process. So you basically, here we talked about how you define a model architecture. Um, this was your data set. These data sets are saved in Keras and PyTorch. We looked at some of the standard data sets. This is a data set with numbers between 1 to 10. We design a network. We use Keras, we use a sequential network, and we add layers to this network. We say add a dense layer, add a convolution layer, things like that. And that is how you construct your model. Um, like this is a convolution layer, where this is a convolution operation that you can do on a input array. So this was your input, and then you did a convolution operation and you reduced the convolution output to something, and this is kind of the output of the filters. Now you design these networks and say, okay, I'm going to have one convolution operation, and then from this convolution operation I'm going to take the maximum of each segment, and then that's called max pooling. And then I'm going to take that max pool representation and do another convolution operation on it, and then I'm going to convert that into a list and then feed that into a linear network that finally will do a prediction. And you define a forward function of how an input data will propagate through this architecture. And once this model is defined, which is essentially like how many layers are there, what the neurons look like, and what is this like flow of operations do I want. Like I could have defined this in any way. I could have defined there are 3 or 4. I could have a 5 FC 5 6. I could have defined many things in my network, but if I do not propagate the information like that, then it doesn't get used. There are different ways of declaring models like this, but in this kind of a formulation, in this forward operation, you would tell what kind of operation happens to the data before you take out a prediction. And then you can, these are some of the standard techniques. You can then say, I'm gonna use a different kind of a layer. I'm gonna design a new layer and put that in here. I'm going to like take only 20% neurons from the first layer, and not the rest of them. So you can design your own weight kind of criterias. You have things like dropout, where it will take randomly certain weights and remove certain weights. But then you can also say, if the weight is above certain value, only then drop out. Different kinds of conditions, and then you can write special layers and special operations and put that in here. And then how the operation works is you have to back propagate this loss. information. So you have to give it a criterion, which is your loss measure. What is this mathematical formula that you're going to use between your prediction and your true label to get this loss difference? And then you are going to define an optimizer. An optimizer is how this gradient is computed. There are different gradient calculation methods, SGD, Adam, R Adam being the most popular one, where it's something like this. You have kind of every iteration you're computing gradients and you're trying to minimize this loss, where your loss is something here, and you take steps each turn, and depending on your learning rate and what kind of optimizer you have used, you will take converge to a solution at a good time, in with efficient computation. And these are a lot of design considerations, and now there are standard formulations for how to do this properly. There is batch normalization and other normalization techniques. So this is very important in deep learning. In general, normalization is critical for performance of models. And normalization, in a broad term, you can look at it in many ways. I can say that my input data, one feature ranges from 0 to 1000, another feature ranges from 0 to 5, another ranges from zero point 0.1 to zero point 0.3. So all of these data features have their own distribution, and there is no like, how do you, when I look at gallons per liter, or I look at a pixel color intensity between 0 to 255, or I look at something like a percentage, I know that okay, a percentage can be between 0 to 100, a ratio can be a 0 to 1, miles per gallon would probably be in the thousands. But how does the network know that these are all different kinds of quantities and they have their own inherent scale? It doesn't. So when we design models, it's up to us to know this and to normalize the inputs suitably. The most common way would be to do like take the mean of a distribution, subtract that, and divide that by a standard deviation, which kind of gives you a normal distribution to your data. Everything ranges between 0 to 1. And this is a kind of a standard technique, because people usually think, or scientists think, that all random processes in nature kind of have a Gaussian or a normal distribution. So you can model any input feature like that using this technique. But then there are many problems which may not be a Gaussian distribution, and you should figure that out before you use this technique. So there is a bit of a caveat to it. You can also do a min-max operation, where you just divide everything by the maximum value, and that will scale between 0 to 1. So I haven't started talking about TensorFlow in specific. We're just kind of still doing a revision of this, these three parts and what all we've covered. I'm gonna get into that soon. So batch normalization and other normalization techniques are very important in the model performance. So when this kind of an input feature you have control over, where your X, you know what this X is, it is a human interpretable thing. And so you can do suitable normalizations like you see fit. But once it goes in the model, and these outputs of these, so this X goes into the model, and after the first layer, there is a kind of a Y prime that comes out. Now, probably this layer doesn't know that this is coming from another layer. For this layer, it is just the same as it being the input. right? So how do we design a method that these values that come out are also normalized when it goes to the next layer? So every layer, when it does this function, feeding and learning process, doesn't have to understand what this data is. It can treat every numerical value just the same. That's the basic idea. So batch normalization is one technique where you take all the activations, the outputs from this layer, and across each feature normalize that, so that this y prime is normalized in a standard fashion. Again, the kind of techniques that we use assume that this will be a Gaussian process, and so on. So we're going to look at TensorFlow today, and a lot of the existing tutorials and material has been kind of become obsolete because TensorFlow 2.0 is a significant change to previous versions. Keras was before an external layer for a bunch of applications or a bunch of libraries, but now TensorFlow has made Keras as a standard kind of an API interface where all of the standard recipes are available through this API. So we did a bit of this last week. We're going to continue with that. Um, we are going to continue with that. These are the most updated resources that's available. I would recommend, if you are interested in learning more about TensorFlow in general and how the core package works, your best bet is to go through the documentation. I'm going to talk a little bit about it, but for the most of this part two, we are going to use Keras and PyTorch, the APIs, and maybe we can use more of the more advanced things in part three if people become comfortable with it by that time. So I shared already the slide deck. It's difficult to copy all of these links, so you can just make a copy of this presentation and then click on these links as I'm talking about them. So this is the tutorial documentation of TensorFlow. That's the most updated, and then there's the documentation. So to give a bit of a background on TensorFlow, let's see. Let me kind of close up what we did last week. So till last week, we were looking at convolution networks and image processing applications. Today, we will look at a regression problem and a kind of a time series problem, which has a sequence to it. In a convolution operation or something that was not so much sequence but relative to each other, like an input image, we convolution operations or CNN is a good architecture. We looked at PyTorch and looked at Keras and how you would do it and load in standard data sets. These are the kind of scripts that we used last week, and that's there in the GitHub repo. So now we're gonna go into TensorFlow and see how to do some of this. We're not gonna look at convolution operations because I think we talked about this enough already. Maybe in the computer vision section, we're gonna solve more problems using TensorFlow for computer vision, but today we are gonna move on to a different architecture that's recurrent neural networks, which looks at a sequential problem. In general, a different concept that's needed for TensorFlow is that of data flow graphs. And you may not need this or need to understand this in depth to use these APIs. And that's the idea. Like a lot of the math and stuff behind this is evolved and can become complex. And if you try to understand everything, you be like waiting for 2 years before you actually start building something. So the best way to learn this is just start solving problems, going through exercises. But it's also good to understand what is happening internally. um, so TensorFlow, what a data flow graph essentially is, and this is kind of um, a concept used more in physics and in things that's not like general programming. Like in general programming, you think of things in terms of RAM, storage, a basic memory block. You say that, okay, I'm executing a main function. I'm leaving this main function to go to another function. So I am saving all the variables in this function in a stack, and I'm going to another function and I'm starting a function stack there, and I'm replicating the variables there, and I'm creating new variables, and everything has its own separate stack. Everything, you have to make sure that if you're processing a lot of data, and if you leave these functions many times and there are many nested functions, then your maximum constraint is running out of runtime memory. And that is the kind of conventional programming that people are used to. But in a data flow kind of an approach, you do not write functions, or you write functions, but you do not like leave blocks of code based on certain conditions, or you do not leave logic um, separate from the data declarations. Things are more in terms of states, where if my input was X, and I do an operation on it, and this operation is OP1, I reach another state which is X2. And I do another set of operations on it and I reach another state X3. I do not redeclare or reassign variables. I do not like put conditions that, okay, if something is under this range, then I'm gonna call this state, else I'm gonna call it that state. No, every kind of operation that can happen is its own results in a state, and this is the kind of concept that you need to do something like some of the more advanced quantum computing kind of applications, where the quantum states is what leads to this computation and a final result output. It You cannot, because a quantum, not to get too much into it, you cannot really control the physical changes that happens to neutrons and protons, or quarks or whatever. You can only do an action on it to take it to a different state, and from these state changes you can manipulate the operation to generate something. You cannot reassign that I'm going to add X amount of energy to this, and then I'm going to decide that based on the state that it reached, whether it's that state or this state, or I'm gonna iterate a for loop on how much energy I'm doing to change it. That's not how that kind of a construct works. So data flow graphs is a basic building block of how you would do something like um, that kind of a computation, and it works well for a neural network flow as well, because when people talk about a network, that is what it inherently is. Everything is a state. You do not, when you have an input or an output, or any of those fixed parameters, they are kind of like fixed states, and you have operations that you do in these neurons, and that leads to another state. And to go from one state to the other state is just a propagation kind of a thing, which is analogous to propagation of energy. And so that kind of a construct helps, and that's why TensorFlow is kind of good to understand if you're gonna in future learn more about, and this is gonna come up, right? Like in 10 years we're probably gonna be using those kinds of technologies a lot more, and right now it's just accessible to a few people, but it's gonna become more and more prevalent. And so TensorFlow is kind of a good way, a good thing to understand to go towards that kind of a programming construct. So essentially, here, this is how you would propagate information, and this is quite a bit different if you really try to understand it. It'd be quite a bit different from what we did before, where these were just operations and functions, and you could do manipulations as you liked, and you didn't really think about what was actually happening. You just declared a class and you defined these defined functions, and you called them and you propagated the data through it. But this is an alternate way of looking at this thing, where what you did was you were inputting some data, you were going to a different state through an operation, and the output of that operation is being propagated to another operation. And this whole you cache a state, you go to another operation, cache the output of that, and then go to the next one. That is kind of architecture internally TensorFlow uses. And but you don't really need to be able to define these blocks and do all of this right away. You can use the Keras API and use an object-oriented programming kind of an interface, and not worry about what is happening internally. But just know that it's pretty cool what you're doing. There's a lot of cool stuff happening, and hundreds of years of math is happening internally. So more about different normalization techniques. Last week, we in the Q&A, we had a good question that what were the other alternatives to batch normalization of the activation outputs in the layers. So these are some of the other alternatives, and I've put links there. And this is very much experimentation, right? Like, we know we need to normalize the outputs of the layers because of what I talked about, that we need to keep everything on the same numerical scale, essentially. But why and how we are going to do this, we can experiment. Batch normalization has its own constraints. Assuming everything has a Gaussian distribution may not always be applicable. When you are scaling everything between 0 to 1, you might reduce certain parameters to very small values, and that might cause some other problems where these weights don't update significantly enough, and it's not learning properly. So then you try out other techniques. Weight normalization is essentially taking a unit vector, where you take the direction and the magnitude of each weight out, and then you can combine that with only a mean based batch normalization, and this technique has found some good applications. Layer normalization is something where when you did a batch normalization in a batch, you took the average of the features in the activation outputs. But in layer normalization, you're going to normalize the features across the input itself, which is kind of like an inverted way of looking at it. And then this one has this so in batch normalization, because everything is from 0 to 1, it has kind of a regularization effect, where when people talk about regularization, they mean that there's a kind of a stochastic noise when you are approximating any physical or observed data to a distribution. When you are and when I say you're mapping something to a distribution, it's this process of doing that scaling, right? When you say I'm gonna do a minus mean by standard deviation, you have already assumed that this is a Gaussian distribution, and that is why I am doing this operation on it. But that assumption is, good and bad. If it is actually a Gaussian, and there is good enough reason that if you had infinite amounts of data, then that's what the distribution would have been. Then it's good. It will regularize the behavior of that data feature. But if it wasn't really a Gaussian, then you can either try to figure out what that true distribution would have been and model it like that, or you can use other techniques. But whenever you are taking a finite data set and mapping it to a distribution, you are adding a stochastic noise to it, which comes from this approximation. Now, this noise sometimes is a good thing, and but sometimes in certain applications, and these blogs kind of touch upon that topic, and there are more research papers that you can read to learn more about it. But there are certain applications where having something like that kind of a noise in your model may not be a very good thing. And for that kind of application, their normalization and some other techniques have worked well. So these are all different things, different concepts that you kind of need to think about when you're designing your own networks. And all of these libraries allow you to define layers and define operations that does each of these things. Another important thing to keep in mind are these metrics. So when you have a model A and a model B, or you have a model A at iteration 10 versus a model A at iteration 100, I can say that the performance of a model when it was trained at epoch 10 is model A, is a completely different model to that model when it has been trained to an epoch 100. These are all valid things. Like, if even if I change the model, when we define it, we are just defining basic architecture of that model, but the actual model that is learned and is deployed and is used, it is not just the architecture, it's all of the hyperparameters that is learned, all the design constraints that went into it to get a benchmark performance. So if I'm releasing a model saying that this has done 85% accuracy on an unseen data set, and this unseen data set is, I assume, is what the production data is going to look like, then I'm benchmarking this model. It's kind of like a feature tag or a versioning kind of a thing. So if that's the model version, then how do I compare that from this version to the next version? There is an improvement, that the next time I do some change to a model, whether it's an architecture change or it's hyperparameter change, how do I say that there is an actual improvement, and before I can actually put it into production? So you need these metrics, and these are not very specific to deep learning, I would think, or any machine learning. These are more statistical approaches. Anytime you do any kind of so is there a version of ROC curve with true negatives on y-axis and false negatives on y-axis? um you you can always do that. Like, it's totally up to you. It's an area doesn't have okay, so an area doesn't have, it's not a vector, it doesn't have a direction to it. If you invert a plot, then instead of having the curve under this one, your curve would be here, and you would take the area under that curve. So ROC is a very direction agnostic, or any of these parameters do not have a direction associated with it. I mean, maybe some people define this as for true negative, false negative, true positive, false positive. You can define your matrix in any way you like. um, it totally depends on your application. So, kind of to talk about it sequentially, so classification accuracy is when you don't care if something being right or something being wrong are equally acceptable. So, if I were to diagnose somebody has cancer, and if I say it's fine if I diagnose this person to have cancer, but he doesn't have cancer, and he goes through this whole chemotherapy process and all of that for no reason, then that's horrible, right? So they're not equally, equally okay to say that this is right and that is wrong. But so in many cases, if I'm going to predict, if someone's gonna say like click on an ad, it might be completely valid to say, I do not want to say that clicking on it has a more weight to it or not clicking on it. I just want to predict if there is a click based on the advertisement quality that I'm putting out there. So there isn't a really bad situation that's going to happen from that. But there are other situations where having a false positive, like a cancer diagnosis, has its very negative implications. Sometimes having a false negative um, has its own very bad repercussions. So if it was the inverted problem, I can also say, does this person not have cancer? And then a false positive is the same as having a false negative. So depending on the question you're asking your model, the consequences will change, and then you can define your confusion matrix to however it's more intuitive for your application. There are standards for it, but I mean, I don't hold anything to a defined structure. Sometimes when it's the true positives and true negatives, that's the performance measure, and these the false negatives and false positives are really dangerous kind of situations. You might want to flip them around to kind of have a visual or measure that strikes out when things are really bad, or in a situation that you did not want that to happen. um, so you can lay out like that, and so basically a precision is looking at that, whether it's a true positive versus all the positives that you predicted, and a recall is a positive versus the true positives and the false negatives, and an F1 score is a combined measure of these two things. And this ROC curve essentially takes, so when I consider something to be true or false, or when there is a prediction, there is always a threshold associated with it. I say that, okay, this is a positive case when the threshold is more than zero point 0.5, or I can also say this is positive when it's more than zero point 0.8. So in sometimes it's a probability, sometimes it's a confidence of a model, that threshold can be of different parameters based on the kind of model you have. But essentially, whenever there is an output like that, or a prediction, or a label that is outputted, there is some kind of a threshold parameter there. And then you can plot a curve where for each different thresholds, you plot um, a curve between your true positive and your false positive. And you could, and because threshold is a continuous value, you could do this for infinite number of points, but generally you don't do that. You kind of do an approximation, or you start off with these extreme cases, where everything that you predicted was completely false, or everything you predicted was completely true. You kind of start with extreme cases and take small steps, and generate a kind of a approximate boundary to it. And this is also kind of an optimization technique. where you take these steps, or you take these optimal points in space, and you figure out this area or this region of operation. And it's there are many other techniques of optimization, but these are some of the conventional ones. So here you would take the area under this curve, and you determine that, okay, this, so my release 1 had a area that was like this, and my release 2 now has a different sort of an area that's lesser than the previous one. So that my version 2, that means that my version 2 is not as good enough my version 1, so I'm not going to release it, or I'm not going to use it. So you compare versions or models or architecture changes, or if you're trying to decide if whether to use 3 layers or 2 layers, or to use a convolution or a multi-layer perceptron to determine between models, you use these kinds of metrics to determine. And it's really like, from what I understand, it's really up to you, and to for you to decide how to best represent this metric to capture the problem and the acceptable solution. Yeah, so I don't know if everybody can see this, but Yelim had a question. Is there a reason for ROC curve with true negatives on the y-axis and false negatives on the x-axis? The reason I ask is the confusion matrix values may not be symmetrical. For example, for car manufacturer, it is more important to know whether a car part will fail. So false negatives are very expensive and lead to recalls. That was the reason for the question. Yeah, so you can follow some of the discussions in this chat. This is a very helpful resource, and depending on, like, really, when you really start to solve a problem, you're not just doing tutorials and exercises and try to learn to use a library, then all of these things become more and more important, right? Like, you might have an intuition that your model is very good, but the metric that you're using does not reflect what you think. So it's then, is your intuition correct or the math correct? You have to, you can explain your intuition if there is a different metric or a different formulation of the metric that can capture your intuition. Then, and if there is a reason and explanation for it, then you can use it, right? So these are some of the things that come with applications and practices, and we'll talk more about this, hopefully, um, when everybody starts doing these things together. So essentially, what here Yelim said is very true, that based on a problem, if my problem was a car manufacturing problem and there was a recall of these parts that failed, and that was a loss to the company, then that is the problem formulation. So you already, based on your intuition and knowing the data and knowing the core area and the problem statement, you know that this kind of a thing exists. So you can then define your ROC curve or your confusion matrix. You can even come up with a singular value to represent this. So what this ROC curve also does, it kind of summarizes this confusion matrix, and it does this over various thresholds. So you can come up with different thresholding techniques. You can come up with different measures that you can summarize a confusion matrix with, based on your application. And that really comes from the domain knowledge, and those kinds of things. And these are mostly for classifications where you have these true and false, negatives and positives in terms of single values, and predictions. In regression problems where it's a continuous output, where you're predicting the temperature, you're predicting profit or loss or sales, and those kinds of continuous ratios and proportions, then you have to use some other metrics like absolute error or squared error or arithmetic. There's a lot of discussion around that as well. And the same, you can, so an absolute error is when you don't consider the sign, like the difference, you do not take that into account, or it's not so important. Where squared error takes an absolute value cross and sums it over a lot of inputs. So it goes, it captures that difference in a kind of a Euclidean way, where if there is a point x and a point y, I can only look at x y value difference and just take whether this y was to the left or to the right of this x. They were to the same in terms of the mean absolute error, but in terms of mean squared error, it's actually the distance value or the length of that line that matters more, and it's over a lot of summations that it will give you this error. And arithmetic is a different way of putting this picture. It looks at the correlation. So if my so in general, if a model predicts something at 50%, then that is as good as a random process. Everything, if it's a 0 and a 1, everything is a likely to have be 0 at 50% chance and 1 at 50% chance. Similarly, any variance around a mean, it's so if my y output seen data or known data was something like I have a distribution between 100 and 1000, and the mean is around 200. I can already imagine what that data looks like. There must be a lot of values near 100 and 300, and lesser number of values between like 500 and 1000, because overall many data points, your mean between 100 and 1000 is 200. So that is the kind of distribution it already has, and you did not need a model or a prediction to know this. So if when you're predicting something, the variance around the mean, and so I can just say that I know the mean of this y from the observed data is to be 200, then why not predict every output to be 200, and that's it. So I'm gonna say every person who walks in the store would likely to spend $200, and I'm going to cater to that customer with that expectation. But that might not be best formulation. That is just the rudimentary of formulation of that problem. So when you do a modeling, when you're trying to solve this problem, your baseline is this mean. I am going to treat this mean observed value as what I could have gotten away with without doing any of this machine learning or any kind of effort. And if you are actually improving the variance with respect to the variance you had with this mean, only then your model is actually doing something for you. Only then it is worth using it. So if the actual observed variance around your prediction is smaller than the prediction around that mean, then that quantity or that model has given you some information. And so relatively, if model A and model A gave you a lesser variance than model B, then model B is better. So those are the kind of relative measures that you can take, and depending on your problem, you can add more metrics and stuff like that if you know a good relation between your y prediction and your y. So these are some of the fundamental concepts. Um, and so moving on, from convolutions to recurrent neural networks, here, like I said before, convolutions are more when it is a fixed image and the data is self-contained and relative. But what about when the one input data itself has a sequential relation with it? Like a video is a sequence of many images. So one happens after the other. Like a sentence, you say certain phrases after certain phrases. You say certain words after certain words. You generally tend to use certain letters after certain letters. So every search, thing that happens in actual process has its own formulation to it. Like there are certain letters that occur more frequently in a language. There are more words that happen more frequently in a language. There is an inherent sequence to words, how they are spoken or written. Then there are, prediction things, like if you're going to predict, say, the climate or the weather or the temperature, and you've recorded previous weather conditions. You know that the summers are hotter, winters, there is a transition between summer to winter, and based on the geographical region, how hot it can get or how cold it can get. So these are inherent properties of the data that you have. And there is, in many kinds of problem formulation, sequence is just an inherent property, like this weather dependency, or a periodic dependency in weather, and then in language and in like different sequential operations. The sequence in the data input is just the nature of the data itself. So how to develop models that takes one input X, and breaks it down into and captures this sequence information as well. So something like this network, where there was no sequence, every input feature, age did not come after income or after employment, or you did not specify that there was a importance difference between these. They were on the same kind of a level. But in an RNN, you are saying that my x1 happens before x2, and all of these things before happen xt, and xt happens before xt1. And so then each, depending on your problem, you can formulate RNNs in different ways. um, you can say that I'm gonna, for every input, and so this whole X is your input. Your entire sentence is your input to the network, or all the weather properties for any given point in time are your input features. So everything is your input, and you just breaking up those features in a way that they have a sequential relation to it. And you can say that I want a prediction for every input feature. So this one gives a very good um, mm, kind of a formula for when to use what. So if I was doing something like a sentiment classification, where a sequence of words or a paragraph or a sentence had a sentiment, like whether this is a negative or a positive, or is it a good review or a bad review, or some kind of a label like that, then you are predicting one kind of an output from this whole sequence. If you are doing something like an entity recognition, where you're trying to recognize all possible entities in this sentence. So like, if you're talking about a city, or if you're talking about a person, based on this input, you're kind of predicting true or false. Is this an entity? Is this a location entity? Is this a person entity? You can have each y can be 0 to 100 categories. What category of entity is this? Or it can just be a 0 to 1. Is this an entity? So every input word has its own output prediction. And then you have things like translation, where maybe every word does not translate to a unique word. You can have a 5-letter sentence in English translate to only a 2-letter sentence in German or something like that. So depending on the kind of problem that you have, you can define different model architectures. And in this kind of a situation, this is your layer, like the every block that you have. So for every input, you have one kind of a layer, and this is slightly different from what you had before. Um, and we talked about these gradient problems before, but this problem becomes more profound in RNNs. This exploding and vanishing gradients come from the back propagation process. And so we talked about last week that when you have a loss and you're propagating the gradients and updating the gradients, and updating the weights in each layer, you're doing this based on the one that comes before it. So from output, I'm updating the previous layer, and then from this layer, the previous layer. You're doing that kind of an operation. And so for every gradient update, it's a cumulative update. Your gradient values can become smaller and smaller if it is a floating point number, and then it can also explode. If it's a greater than one value, it can also become very big when you're doing this activation operation and multiplication of weights and things like that. So this problem becomes more profound in RNN, because then each of this back propagation here happens based on the sequence. So if you have a 20 sequence input, you're going to essentially do a 20 times back propagation. Because the y prediction of yt plus 1, it's possible that this prediction is based on this xt, the xt plus 1, x up to x1. So all of the inputs before can lead to the final prediction, and yt can depend on xt and everything before it, and then y2 can only depend on x1 and y1. So there is a propagation, and the more number of layers in the sequence, the more chance of these gradients to vanish and problems to arise. So this problem becomes more profound in these kinds of sequential architectures. There are a couple of techniques like gradient clipping, where if some gradient is becoming too large, you can just clip it at a certain value so that it doesn't explode. This is a crude method. There are more techniques associated, but it also works pretty well. And then other approaches to solve this would be to have a different activation. Like this problem is more prevalent in things like sigmoid, which has reduces weights to a more smaller value. ReLU is more of a linear operation, so it reduces this problem. And then you can have residual networks, where there's a residual connection between weights and neurons. And so it's kind of like when you divide something by a number, and you always add an epsilon to it, so something does not become zero. It's kind of a similar concept of residual networks, where you have this constant value that you're keeping in the network, so to control this behavior. And this is kind of one step towards a model change that can happen, and that can control this problem. A big step in this model change is something like LSTM network. An RNN is a basic building block of a sequential model. LSTM is a more advanced one, where it kind of does this consideration that it should not explode these gradients or vanish them, and so it keeps this state C as a stored kind of a connection, and it propagates through the back propagation and the learning process. And the weights that are stored, it kind of stores the long-term relationships, and the states kind of store the short-term relationships. You can find more details here, but and generally what you're doing is, if this was so your each prediction, and so here when you did a loss or a prediction y1, you had a true label. When you, in the training process, you had a true y1, what it should have been. If you were doing a translation, you have a good translation output, and then you know what your y x what should have been in that position. Or if you're doing a prediction of this is an entity, this is a name, what kind of name it is, or something like that, you have a label associated. So you're doing a loss calculation at each of these inputs, and then the total loss here is a cumulative sum of all of them. So you're in a general RNN block, you're doing a cumulative sum of each of these various. In LSTM, the loss computation is modified so that when you do a back propagation, you have something to a different kind of a path that controls this vanishing gradient issues. Here you have three matrices that from this state C, it generates, and then, or it learns, and then you have one for H. And so there is a long-term and a short-term dependency that's learned here, and then both of them kind of combine to give you a loss. So if you want to learn more details of that, you should read these articles. And so in general, LSTMs are a good network, basic architecture to solve the sequential problems. Generally, people don't use vanilla RNNs because of the different problems associated with it. And so we are gonna today work on some notebooks and formulas that look at this kind of a problem formulation. So kind of to start off with basics in TensorFlow, and if people have done PyTorch and Keras exercises from the last 2 weeks, all of this should look very familiar. TensorFlow also is kind of like NumPy, and like how PyTorch is a wrapper around NumPy, so is TensorFlow. Many of the operations that you do in NumPy you can do with this, but I think there is a slightly lesser flexibility, but also the assumption is that most of the kind of data processing and transformation pipelines that we talked about before, most people end up using NumPy and Pandas to do that kind of a workflow anyway. So there is lesser and lesser need of TensorFlow to have implemented all of these features. So basically, when you are defining an array in TensorFlow, it looks like something like that. You can define how many, whatever you want to add. It's a basic array. And so it will give you the shape and the data type as its properties. These are very similar to things you have seen already. And then there are operations like matrix multiplications. And if you don't know what a matrix multiplication is, it's like 1 times 3 plus 2 times 0 is that summation is the output of this first indices in that output. So that's a matrix multiplication. A lot of the matrix operations that we do are this. And so you can write transformations, you can write matrix algebra using these, and the core packages, you can find them in the docs. And it's not even necessary with TensorFlow that you only do deep learning or neural networks. If you understand this data flow problem construct, and there are many other non-compilable like languages that do similar kind of things, you can use TensorFlow to solve those kinds of problems as well. Like different kinds of graph computations. There's things like Elixir, which also do very similar things. And you can solve those problems using TensorFlow and some of its core functionalities. But for deep learning, we are moving more and more away from the generic uses, and using Keras and its defined layers, and trying to combine different existing things to make something. So yeah, so a constant is like defining a kind of a node in that data flow graph, where you're not updating something in that value. It's kind of like a static value. And if it is a updatable value and has a gradient to it, you can call it as a parameter or a variable. And zeros is like defining a blank array. And this is a standard way of Keras layer definition. You can also like write your own customized layers, where you inherit from this Keras layers, something like you did before with the NN module, inherit from a predefined network. Similarly, you can inherit from a predefined layer architecture, but then you can modify what happens inside of it. So if you were to rewrite a convolution operation, you could define a different kind of a kernel, where it's not something that exists out there. Maybe there is a color intensity or a red detection if you were doing something like a biomedical application, and you had images where red cells versus blue cells versus green cells. Those transitions were more important. Then you could define color based filters of what kind of red intensity was bad, or you were trying to capture from your convolution inputs. So you wanted to probably capture these very red pixel cells, and very blue pixel cells, and those were more pertinent or more relevant information for your network. So you can define then different convolution operations inside this, and use all of the other functionalities that a layer comes with by default, but then change the internal operations. And then similar to PyTorch, forward in TensorFlow and Keras is call. And so when you call it, it's the same thing as propagating that information through that layer. And then same with networks. You can, as you did with NN module, you can do a TF Keras start model, and that one is a basic neural net functionalities, where again call is same as forward, and then you can combine. So instead of using a model or a network architecture that's predefined, you can define your own. You can say you're going to do a convolution, then you're going to do a batch normalization, another convolution, and that's how you're going to propagate the data before you take a prediction out. Or you can also use the Keras sequential kind of a layer-based method of declaring networks, where you tell all the operations, and the sequence in which you declare them in this list is the sequence in which they get performed. So in this kind of a method, you can define conv b before conv a, and conv c first. It wouldn't matter as long as the sequence in which the operations were to be performed is what you designed it to be. But here you have to mention the sequence of operations in the sequence you want this call function to execute it. And so similarly, you have a learning process, an optimizer, and you train it, and you take the metrics and you judge the model. Um, and so I wanted, this is a really interesting article. I found this is PyTorch implementation of an LSTM cell. A lot of the times people don't look at what LSTM looks like internally, but if you go through this notebook, and this is all shared in the GitHub repo, if you look at this will give you some understanding of how to convert mathematical functions to like code in that's executable in PyTorch. So here, I would really recommend that you read this article and see how they are translating each of these mathematical operations into a function here. So essentially, in an LSTM, what you did was there are three kinds of gates or three kinds of functions. They're similar to activations or similar to like saying layer, this node has this kind of an activation function, this other layer has a different activation function. So similarly, you can think about inside this LSTM cells, there are three kind of different gates that forms this composite operation that happens on it. In the first gate, you have an X, and so H of T is something that is carried forward from the previous block. So this is just an exit block, and there is another block before it and another block after it. And so H of T minus 1 and C of T minus 1 are two things that have propagated from the previous block. And when people talk about these architectures, they often refer to these blocks as time instances, and that kind of confuses people. It really depends on the problem, if it's truly time like we mean it, or is it just a method of saying here time really means a sequence, because this sequence came before this sequence, and then this sequence comes before the next sequence. Because of this chain of operations, people associate time to it. It's not necessary that the sentence itself was recorded or was inputted at different points in time or in different operations. It is one input is just even if you can recording something, that first word is spoken before the second word, or this temperature measurement is taken at 1 second before this. So sometimes it converts to real time, and sometimes you kind of have to fit that idea to a problem. But time, don't get confused about what that means. So essentially, that T minus 1 is the previous block, and the current block is T, and the next block is T plus 1. And here you have some state information from the previous one. You have a new input information, and you're doing some function here, and you're coming up with an intermediate result. Then you have another information, which is an input gate, and you're trying to store some information, and you're trying to determine how much of the previous state to remember and how much to forget. And then a final output is a mathematical combination of these two. So the idea here is that the prediction of my current input, or the xt input, is not only dependent on my current input only, it also depends on the previous input. So if I said I like to eat, there is probably going to be a name, a word after this, which is a kind of a food. And so there is an inherent pattern there that, through the learning process, it can learn that this food word will come after eat, uh, to will come after like, and so to predict the output of an input, like just to is not enough, you need to know what came before it. So this sequential dependency is important. We are going to talk more about this um, in part two, where we break down natural language problems and stuff like that. But so this is kind of a mathematical formulation of all the three kind of steps that it has taken. It has taken the input, done some math on it. It has taken some previous input and done some math on it and combined the two to come up with an output. And so each of those functions in that article now is declared in this model, and when they defined this custom LSTM block, they are defining that in this is also a network. And so a network can be a bunch of LSTM blocks together that does one function, but a network can also be one LSTM block that does only one thing. And so you do not necessarily have to know what happened before and after to think of this as its own separate problem. You can define it the same way. You take an N module as the base, and then you define what are all the operations are going to happen in this. Initialization of weights is this is kind of a default implementation. And this is also a another normalization distribution kind of a discussion, where if you randomly initialized all weights, and it could be any value, be it 1000 or be it 0.1, then that random initialization is not going to learn quickly and not going to learn well. So there has to be a good distribution of those weights when it's randomly initializing things. And there is a person who came up with this technique, and then there's more literature around it, but generally this is how you initialize the weights of a model. And then how this information is propagating in within an LSTM blocks through these three operations, and then what you can do to change any of these operations, do it differently, build your own custom LSTM block that's kind of defined in this code, and it gives you a very good understanding of how you would do something like this yourself if you needed to. So today we are going to have about half an hour. We're going to look at some regression problems in Keras and TensorFlow. And we're also going to look at some generalization discussion. So at this point, does anyone have any questions? Okay. Okay, so let's save these discussions for the end, for just to like have a beginning to an end to the topic. So something like this, and this comes from this machine learning mastery blog, and I'm gonna also use something from a TensorFlow collab, and I would suggest you run this with me. And this is a pollution data set that you can download from here. If you click the link on this on this notebook, it should open up, and then this is what the data looks like. The raw data you can see has a lot of nan values, which are like either not defined or it was not recorded, something like that. So in real world data comes in a kind of a messy way. So you have to clean this data, and there are different ways of doing that. So here, when that data came, it had a year, a month, a day, an hour kind of parameters. So you can do different operations on it to convert it to a unified date, just to have like a timestamp kind of a thing. If you only cared about the hour of the day, and you wanted to like remove everything else, you could just keep it like that and use that as a feature, or something like that. Given um, temperatures, would you like to predict the hour of the day, some problem like that. So depending on what the problem formulation is, you can do different operations here. Date itself is not a feature. Date is kind of like an index, or giving a unique value to each row. So each of these measurements happen at a distinct point in time, and so you are taking that date and in using that as an index, or using is that as a ID of each of these rows. Um, Now, this is something like domain information transfer, where your data set had different feature variable declarations, but then from, for better understanding and from your domain knowledge, you can convert them to what these actually mean in more natural terms. Now, drop NA is an operation that will drop all the rows that have any one feature that is not defined. So I see there's about 2000 rows that have corrupted data or something like that, and you can either remove them completely, or you can keep them and just replace the zeros for these values. You can do it as you like, and also can try different techniques and see the performance. So this is kind of a cleaning operation, and you save a cleaned data set. Then you have to now convert this into a feature representation. You drop the dates and you just keep the features. You can plot the features and see what this looks like. This looks like a very periodic thing. This data set also kind of looks like artificially generated. It's very unlikely that all of these parameters will have sinusoidal um, nature to them, but whatever, you can see how the different features look like by themselves. In the next one, you can also look at how features are correlated and correlated to your prediction parameter. So here it's difficult to say if there is a defined kind of a relation between it. Like, this is pollution is my target variable. If I saw that every time my dew was on the high, my pollution was also on the high, and every time my dew was low, pollution was also low, then that be a kind of a visual correlation that I could see, and that means that dew becomes a very important feature for the prediction of pollution. And but right now we cannot really understand if there is something like that. We can see that when the dew and temperature are high, pressure seems to be low. They're in opposite cycles. We can see that when these are high, this rain happens more. When pressure is high and the temperature is low, the rain is not there. So some of the features have different kinds of interdependencies, which kind of makes sense as well. Like, when there is rain, it's probably not snowing. When there is high temperature, then possibly, or like a pressure drop, then rain probably will occur. So those kinds of things, but we do not see that there is a clear determination of the pollution continuous value just by looking at this. But it makes a sense that since these are all interdependent quantities and these affect the weather conditions, it will affect pollution. There can also be some hidden features, like when it rains, maybe cars stop and a lot of people are not driving. When it snow, the driving is less, but then there are houses that are emitting smoke from heating systems. So all these implicit features that are not captured or not recorded, they also affect pollution, but we can only predict something based on what can be measured, and hopefully in the cycles and patterns that these capture, the implicit dependencies are also kind of also gets modeled in that problem. um, so now you have to convert this problem into a series problem, where each of this parameter, it comes one after the other and it's a sequence of data points. So this is a kind of a series to supervised learning problem technique that they've showed in that article. So when you do that, you are converting this data to a previous to current time step kind of a thing, because your current um, prediction output is your tth, and everything that was recorded was kind of like a t minus 1. That's the inherent assumption here. um, and now you can separate out. So this, all of this is the complete data set. You do not have a train data and test data in the way it was loaded like you did in the previous sessions. Now it's up to you how you want to split this data. There are like different libraries like NumPy and scikit-learn that gives you different ways to split data, random splitting and things like that. But one important thing to consider is for sequential operations, you do not want uh, the sequence information to get lost. You want to train the model in the sequence that the data is recorded. So you want to capture this sequence relation between the input features. So by that I mean there is a dependence of this feature and this feature, but there is also a function within this feature where values were high at certain times and values were low at certain times, and there is this time sequence to that thing. So here you do not randomize the input in terms of the sequence that they are recorded in. You keep that the same, and in case your input data does not capture the sequence, the correct sequence in time, you should model or you should clean that data so that everything happens in sequence. One way you would do that is you would convert each timestamp to a Unix time, which will give you a continuous value, and then you can sort that from lowest to highest, and then again convert to date. So that will sort out all your input data in terms of the way they occurred. And then you can split your this is the pollution data set. And so we can see that there's year 2010 to 2014, so 5 years of data. And now you can split your data set as how you like. In this problem, you can train it on 2 years and then predict for the next three, train it on 4, predict it on the current year. You could then change this formulation to something like a monthly or hourly problem, where you predict you train everything on for the last month, and you're only trying to use the current months to use the prediction and the test. So here, um, then you can split this continuous data, and because the sequence is important, you're gonna split it based on index, and you're gonna define what index. Here you're just taking 365 times 24. So because your each timestamp is 1 hour, you're just taking all the data from 1 year, the first year, as your training data. And so you can see your training data is 87 something, and your test data is 32 something, which is like not ideal. You cannot really train something for 1 year and then predict many years after that what is going to happen. Uh, you should at least have the last year's prediction for current years, and then assimilate current year and previous years as the next train data to then predict the current years, and go on like that. But let's see what would happen in that case. And it's also possible that it's not too bad. Like maybe it's a place where the weather doesn't really change very much. So even if you have learned by hour pollution measures relation with other parameters for 1 year, maybe it will generalize, and it won't be that bad for all of the years. So in some cases, like in a computer vision application, you cannot really train something on 87,000 images and say the distribution of that data was very different and test it on so much. Um, but then it also depends, like for weather data, if all the data points are very similar to each other, it doesn't vary in time or vary between each other, then it's okay. So we can try different data partitions. Here we have a sequential network. We've added an LSTM. This is just a single LSTM layer with the 50 LSTM blocks. And then it goes into a dense layer, and then there is an optimizer, um, and using Adam optimization and a absolute error loss metric. We're going to fit that model, and we're going to take the loss and the validation loss and print that out. And so here we're just inverting the prediction and the true labels to just get this mean squared error matrix calculation. And we are printing out the um, RMSE value, which is like in a regression case with the metric or the accuracy kind of a thing. We can also plot the predictions versus the true values. We can see that at least it captures this linear relation, right? So if every true value was extremely accurately calculated, then the predictions and the true values will have y equals x line, which will be this line, a diagonal line. So that would mean you have 100% accuracy or a very good model. But in this case, we see a divergence around that y equals x line. And so it's not very good, but it's not terrible. At least it's capturing the y equals x relationship in somewhat. If it was like a perpendicular degree or like a parabolic function or some very random dots, that would mean that it has learned no pattern from this process. and then you would need to change your architecture significantly. Here, let's try doing 3 years of data to predict the rest. So now we have a 26,000 and a 15,000 split, and the same thing. So for this one, you're gonna see that the loss significantly decreases for, by using um, this information for more number of years. It generalizes better, um, but it's not really very good, or neither it's a very optimized model. You can try out different architectures, different number of layers, different data partitions to see if you can improve on it. So here the RMSE is 21, before it was 26. So there is a difference there in using different kind of data partitions. This one, we kind of look at different ways of analyzing data. This is from this collab that Google has put in their documentation. And one good way of downloading any data from any kind of web browser. So you have a lot of open source data sets. You have Google data sets, search, where you can find lots of data sets. You have Kaggle and things like that, where you can search for different things. And so once you have a path to a data set, you can just put that path here and put the folder path for on your local system and get that file. Now this is a miles per gallon prediction, where your input features of this car is the horsepower, weight of the car, displacement, cylinders, acceleration, model year, and then this origin is the country where this car was produced. So from here you can see that model year, what does that really mean? Origin 1, 2, 3, what does that really mean? Those are very different things from weight, acceleration, horsepower. These all seem to be numerical floating point numbers. And then cylinders is kind of a constant or a fixed number of values. You can only have a 4-cylinder engine, or maybe 2 or an 8. So there is a deterministic thing here. And then miles per gallon is also a continuous kind of a space. So to kind of model this problem, you need to get everything on the same kind of an inference level. And so firstly, you look at origin, where in this data set you only have 3 countries, where from domain information you know that 1 is USA, 2 is Europe, and 3 is Japan. And so those are the main 3 car manufacturing companies. So you have mapped this 0, 1, 2, 3 to the original ones, and then you are making this into its own separate feature. You're breaking down this one column into 3 different. Is this car European? Is it Japanese? Is it in US? So you kind of have broken down a categorical variable into these hard encoding vectors. And another way of doing that in Keras would be through this to categorical call. You could, if you had a NumPy array instead of PyTorch and Pandas data frame, you could do something like this. And so now we are trying to plot what the correlation between these different features are. So this is kind of like how each of these feature relationships vary with respect to each other. Here we kind of looked ourselves and made those derivations. Okay, that there's these relations between the individual features, but Seaborn has this pair plot, and you can always look at the documentation, and it will tell you what exactly it is showing. Um, So this one gives a self distribution. This is what it looks like, and then what does MPG look like with respect to cylinders? What does cylinders look like with respect to displacement? What is the interrelation between these variables? It will capture in this kind of a plot, and you want to look at this so that you can normalize things if necessary in a different way. You can possibly like select features and remove certain features that you do not think are relevant. So if MPG does not have any sort of relationship with a certain parameter, it also kind of means that that parameter is not affecting the prediction of that MPG. So then you do not necessarily use that feature if it's not uh, having any relation with your other parameters or with your predicted target parameter. Then uh, don't consider it for the problem, or you can experiment with it. So this is kind of a feature engineering recursive process. This kind of gives you the means and standard deviations of each of these parameters. If something does not vary at all, so there is a saying like if something is always deterministic, something has 100% probability of happening, then that is not information, right? So if all my recorded data had 4 cylinders, then I'm not going to use that as a feature. And if it's expected that all my test data or all my real world data is also going to be 4 cylinders, then I really don't care about it. But if it turns out that my production or my test data has things of 8 cylinders and other kinds of things, then you might want to augment your data set so that every kind of parameter that you have in your training captures the distribution in your real world. So now you normalize, and you're dropping this whatever you're predicting that thing out of your feature. You're normalizing with your mean and your standard deviation, the same thing like modeling it as a Gaussian distribution. And then you are building a model with sequential 2 dense layers. This is a simple model architecture. Um, and then you're using RMS prop as the optimizer and computing an MSE loss. You're going to print out both the absolute error and the squared error for this run. And then the model here with the summary call will tell you all the definitions it has. And now you're training it with these parameters. In TensorFlow 0.2, you have a unified fit call where you can put the number of epochs, your validation split if you want to have that, whether you want to print out these statements, and then your data, your labels into one function call instead of having a separate loop for it that you wrote yourself. So now we are looking at how this MAE and MSE varied. And the point of this exercise is to know how much to train and how long to train. In this case, you can see that the validation output saturates like after a certain point, and then it starts to kind of increase after it decreased significantly. So it's important to like understand and debug these curves, because this is most of the like real world training and application that you will do. So you can, and this understanding, so if you have a network that has say about 100 weights and parameters that it can train, and give it any data set, right, it will learn to 100% accuracy, um, the input data, because it has enough weights. It will keep tweaking its parameters till it fits everything in its training data. But it's not what you want. That is not necessarily a good thing, because your training data is not all the data that there is, and there is this generalization aspect, and so the validation loss captures this. So you should have a good train validation split, so that the model does not see this validation data while it's training, but you get an in-time measurement of is this generalization as the training progresses. And if you're seeing that at this point my loss kind of training loss hits a minimum, but and the training loss kind of keeps on decreasing, but my validation loss from this point on increases till it saturates somewhere, then this is the kind of point that you want to stop at, or this is the model version that you stop at. So like I said, this model architecture won't change, but you can have a model that's trained to epoch 100, or that's trained to epoch 10. And these are two versions of this model. The model that you should choose to use or to deploy should be something here, where you had a validation performance which was as good as the training performance. There is no point in keep training and keep decreasing that loss if you're not generalizing. Um, if you have a lot of data, and you have this understanding that you have come up with a lot of the data that this system is going to see in the real world, then maybe there is some value there still to learn to a certain extent, and maybe do a compromise, of something like that. That's not too bad on the validation, but still lower than something previously, and you can do a trade-off there. But in general, and if you especially have less data, then this is the kind of way to do it, where you would stop your training or version your model at a point where your validation loss was the lowest. So early stopping is something that can do this by itself. So you can keep training something for 500 or whatever you wanted, and there's of course a computation cost associated with that. If you're doing this on more data on a GPU, there's like a cloud cost and stuff like that. So you want to stop it at a reasonable time in an automatic basis, maybe once after you have done like a general formulation and have seen this, you have determined a value for this, or you're gonna use this early stopping criteria inside of Keras, and say based on my validation loss, have a wait till at least 10 epochs till you do this is your maximum, and I could put this as 50 or 100, or some till how much it needed to compute before it compute the minimum. So now it's gonna compute 10 epochs and then see what was that epoch that was the minimum and stop there. So in this callback, you can put this early stop condition, and then this will do that automatically for you. And so you then see that the validation loss and training loss kind of stay close to each other after that. Um, and these are your final predictions. You see this model does pretty well. It captures the true prediction and predicted uh, label quite well. This is the prediction output distribution. So, if every output or every value in your output was equally likely, and was predicted equal number of times, that's like a uniform prediction distribution. But if some values are more likely to be predicted, then those are at a higher level, and some values are inherently not there, so some values are never predicted. So in if your data was infinite and if your modeling and all your intuitions was correct, you would have a Gaussian distribution here where you would have this mean value at something like 0, and then it dispersed in standard deviations. But in real world it doesn't happen. But this is good enough. If you had a uniform, then maybe something is still like not right, unless it's very likely that you're going to have equal probability of everything happening. Yes. Okay, so we are at 12:05. Um, so this is a good collab, and it has a lot of good discussions on this generalization, and different other techniques. I've linked that to the slide here. um, Here, so this is also a good blog that just describes what I talked about, where you have this performance where you are getting this validation where it's starting to overfit, where the training keeps decreasing, and there's this perfect region where you stop. You can also then give it conditions to early stop, and then you can try out this collab yourself, and we can discuss this more next week. Right.
Hello, sir.
Yes.
Sorry,
pardon me.
but I'm just running about an environment. I'm running a VM with just 2 cores, but are there any free resources like Google Colab? I think a year or 2 ago, I seem to recall that they offered, I don't know, GPU access or something. I'm just wondering, could you take a moment just for starting out, what environment you might recommend, what you use?
Yeah, so these collabs have their environment set up. You're doing this on the cloud. You can use GPU, and these collabs that Google publishes or something, you can have that option. To do it here, you don't need any personal resources for that. You also have a thing like Quick Labs. Quick Labs is also a cloud-based learning environment, where all of these collabs, and not just Google Cloud and TensorFlow, but a lot of uh, other people as well have shared resources and tutorials. So this is another one.
Yeah. Okay. I know. Yeah. Sorry. What's the? Oh, I've forgotten now the name. But in any case, yeah. Okay. So there are free resources, including Google Colab. So, and the Quick Labs, yeah, through Greg Bennett at GDG YYC. I know he runs those study jams. So yeah. Okay. Good. Thank you very much for that.
Yeah, and we're gonna do some of GCP itself. If no one's used the architecture or like the framework outside of Quick Labs before, we are going to use this. So if you set up a new account, you get free 300 credits, and we are going to try and set up a VM and like a virtual machine, configure it with GPUs, and do everything from scratch in part 2. And anybody with a new email ID, if you register, you get $300 of free credits to test things. So we're going to use that, and potentially we also have some cloud credits that we can avail. We have to talk to Greg about that.
Okay, so stay tuned. That's great. Thank
Yeah.
you very much.
Yeah. So I linked those in the meetup page. I'm gonna send that out again. So this is essentially this series will have this YouTube channel for it. Yes, it has to be a Gmail account. And if you have already a Gmail account that you have used GCP with before, then use a different one to get those 300 credits. Like you can get that only one time. So that's going to be the YouTube channel for all these recordings. But I'm also thinking I'm gonna upload session videos after each part, because then people are like, we're not going to attend the sessions and we're just going to look at the videos, which is not as effective. Also, this part was more about me giving lectures and telling, just general stuff. But from the next part, I'm really planning to have interactive sessions where I state out problem statements and we go through that thinking process and trying out different steps. And so each topic, we probably gonna talk a little bit about natural language and computer vision and define some base problems in like an hour or something. And then after that, I'll solve kind of a problem. And the next week after that, I would want a like a group session where people come up with ideas and solve problems, because that's really the only way to learn. So I'm probably gonna delay uploading videos so that people attend. Yeah. So thank you. If there are questions I'm missing, I'm gonna post answers for them in the meetup channel. Thank you, everybody.